Hey guys, Mr. Brown here, and in this video we are going to be talking about how we predict the relative strength of different acids if we're not provided with a pKa table. And we may want to do this to try to determine whether one acid is relatively stronger, by which we mean is it easier to give away its hydrogen ion, its proton, than another molecule to a particular base. And we are going to do that using a method that is called the ARIO method. And when we're implementing the ARIO method, often what we are doing is looking at the lone pair negative or negative formal charge formed on the bases, or the one that is already on the base in an acid and base system, and trying to determine where the negative charge is more stable, and stability of a negative charge leads to a molecule that is a low pKa. It's easy to give away the proton. It has a lot of acidic character. And we can use that to predict the position of equilibrium as well, where we always predict that equilibrium will favor a more stable lone pair or negative charge. And again, we do this with a method called the ARIO method, and it stands for atoms, resonance, induction, and orbitals. And we are going to consider each of these things in order to try to determine how stable a particular negative charge is. And of course, we'll take a look at some examples. So we start with the atoms. The first thing you look at is, for example, if you're given a question that says, you're given these two compounds, ethanol and propylene, which has a higher relative pKa, or which has a relative lower pKa. How do their pKa's compare? Might be something we're asked. And when we're asked a question like that, we're being asked which one would be more likely to give away the proton, and specifically the proton indicated. And so if we're trying to figure that out, what we're going to consider is what happens when we take away the proton, and we see the result of that action here. No matter which one, either one of these acids react, or no matter what kind of base each of these acids would react with, the end result would be these ions here. And we can see that in the case of ethanol, if we remove that proton, it becomes an ethoxide ion, where the negative formal charge in the lone pair of electrons is located on an oxygen atom. And in the case of propylene, if we remove the indicated hydrogen, then the lone pair of electrons is located and resides on a carbon atom. Now, I'll go ahead and point this out, even though we're not going to mention it until next. Notice there is some resonance for that lone pair, so that would help stabilize it. But ultimately, it resides on a carbon atom, and we know that oxygen is more electronegative than carbon, so the negative charge is more balanced on the oxygen. So what that means is ethanol, it's easier for ethanol to give up that proton, much easier for ethanol to give up that proton than it is for propylene, because oxygen can handle negative charges. Carbon does not like negative charges. And furthermore, what that means is this would have a lower pKa. Remember, we like to think of pKa as kind of a rating for how likely or how much hydrogen wants to be in that particular location, and a higher pKa for the propylene molecule. Now notice and take into account, this doesn't always follow electronegativity. For the second row elements, it does follow electronegativity. We would say that negative charges would like to be on oxygen more than nitrogen, which would like to be on nitrogen more than carbon, and of course oxygen more than carbon. But in the same column, and the one you have to worry about most is sulfur, negative charges are actually a little more balanced on sulfur than they are on oxygen. So if you were to compare sulfur and oxygen, the sulfur would always win. Because sulfur is a bigger atom, it's more able to balance the negative charge. Even though oxygen does have a higher electronegativity, it pulls harder on the electrons. Sulfur is better able to balance that negative charge. And so you always go with atoms first. And that's if there's a difference in atom, you can immediately make a determination as to whether a particular negative charge is more stable. And stable bases are mean that you have a weak base. A stable base is a weak base, and it comes from a strong acid. An unstable base, like in the case of propylene, carbanions are very unstable. They look to react and fill that bond very quickly, are very strong bases, and come from very weak acids with very high pKa's. So moving on, the next consideration is what happens if these electrons do end up on, say, both on an oxygen. And the next consideration there is our good friend resonance. Do either of the lone pairs have resonance? And of course we have a consideration here. Ethanol versus acetic acid. And again, is this proton, considering this proton here, which of these molecules has a lower relative pKa, which is more acidic? And so again, we consider the conjugate bases that are formed when the proton is removed from each of these molecules. And in the case of ethanol, we have a lone pair that is localized to one oxygen, and the negative charge is localized to one oxygen. In the case of acetic acid, hint, it's in the name, the negative lone pair is actually stabilized by the fact it resonates over two different oxygen atoms. So we can show that lone pair being associated with two different oxygen atoms, and resonance of a lone pair leads to stability. Lone pairs that have more resonance versus lone pairs that have no or less resonance are more stable than, or lone pairs with more resonance are more stable than lone pairs with less or no resonance. So what that means is acetic acid, that negative charge is very stable. So this molecule here, its conjugate base, is very stable. It's a weak base. It doesn't need that negative charge is pretty balanced out of those two oxygens. It doesn't need to go out and replace the hydrogen very quick. So this is a weak base. This is a strong acid with a low pKa. This is a strong base. This is a weak acid with a high pKa. And hopefully that relationship makes sense to you. The next consideration, what if the electrons are on the same atom and have the same resonance, or neither have any resonance? Because most times you'll run into this case on carbons kind of with no resonance, honestly. But what if the electrons are on the same atom and there is no resonance, or they have the same resonance? One thing you can look to is induction. Are there any groups nearby that help shoulder that negative charge, even if there is no resonance? So we have an example here is from acetic acid and something called trichloroacetic acid. And as you can see, in acetic acid, or regular acetic acid has a methyl group here, so there are 3 implicit hydrogens here. So the only difference between these two molecules is those 3 implicit hydrogens have now been replaced with chlorines instead of hydrogens. And we know that chlorines, or keep in mind, chlorines have lone pairs of electrons, but chlorines are also kind of large atoms with lots of protons as well. And so what we find is, if we look at their conjugate bases, each conjugate base has the same resonance. So they would both have the lone pair resonating over 2 oxygens. But the chlorines here, they can help stabilize that negative charge even further than these dinky little hydrogens here in this position. We got big atoms over here that can shoulder some of the electron density that's involved with the extra lone pair there. So the trichloro version of acetic acid is more acidic. In fact, you can see the pKa's as they go down as you replace one of the hydrogens here, 2 of the hydrogens here, and 3 of the hydrogens there. And finally, in the last version, or the last part of the ARIO method, is the orbitals. And I should have said this a moment ago. This is actually the one that you see mainly with carbon atoms. And that is, so when a carbon atom, or sometimes when comparing particular carbon atoms, whether it's easier to remove a proton, we look at the hybridization of the lone pair's orbitals for that particular carbon. And we have a comparison here just at 2 different ends of the molecule. And we have in the red proton here, we see that when we remove it, we have a lone pair of electrons in an sp2 orbital. And when we have the blue proton removed, we have a lone pair of electrons in an sp orbital right there. We can see that the sp orbital is shorter and more spherical. So that's held closer to the nucleus, and that makes that lone pair of electrons right there more stable than that lone pair of electrons right there. And we see that there's a difference in pKa. So single bonds lead to the least stable. sp3 orbitals, sp3 hybridized carbons, lead to the least stable bases, and their conjugate acids, which are just regular single bond hydrocarbons, have the highest pKa's. These things do not want to give up their protons to anything else. If we have a double bond, it makes it a little bit better. So taking one of these hydrogens off is a little bit easier, and the pKa is a little bit lower, because that pair of electrons would be in an orbital like that is a little closer to the nucleus. For the acetylene molecule here, where we have a hydrogen next to a triple bond, that means the removal of the proton leads to a lone pair that is in this orbital here, held closest to the nucleus of all those compared orbitals, making it the most stable, making it the most acidic, making it have the lowest pKa, making it easiest for it to give away that molecule. So that's the ARIO method. Those are some considerations we can take when trying to determine relative strengths of acids and sometimes equilibrium positions of acid and base systems. And of course, I'll have some examples coming up for you next.